Number 8, we're asked to use transformation rules to sketch a picture. So the way I taught it was to use a mapping of the parent function and identify changes that happen to the original parent graph. So what I want to do is I want to quickly remind myself of the parent graph. So in this case, it is based off of the square root of x. And so we talked about some critical points that are worth knowing. So for example, we know it goes through 0, 0. We know it goes through 1, 1. We know it goes through 4, 2. And then what I want to do is I want to look at the transformation rules and what changes what. So to start off with, I'm looking for the inside of the square root, and that's going to tell me how the x's change. And it's opposite of what I see. So if I see a plus 6, that really means I'm going to subtract 6 from the x's. And then I'm going to go to the y's, and same thing. Anything that's being multiplied on the outside is going to change the y, and anything that's being added or subtracted will change the y's. Okay. So, and one idea that's actually not too bad is once you've figured out what the parent graph looks like, you can actually go in and replace the square root with the letter y, and that tells you what the mapping is for, at least the y component. Okay, so then from here, I'm just going to plug in those 2 points into these transformation rules, and that'll give me a new point. So 0 minus 6 is negative 6, 1 minus 6 is negative 5, and 4 minus 6 is negative 2. And then same thing for the 3y plus 3, so 3 times 0 plus 3 is 3, 3 times 1 plus 3 is 6, and 3 times 2 plus 3 is 9. Okay, so then I'm going to come in and plot my points. So negative 6, 3, 1, 2, 3, 4, 5, 6, 1, 2, 3, right there. Negative 5, 6. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. And then negative 2, 9, which might not be on my grid, but that's okay. Negative 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. So right there. Okay, so that's what that particular graph looks like. Scroll down to the next one. Okay, so what is the parent graph? Parent graph is x cubed. And so then I'm going to make a list of all of my critical points that are based off of x cubed. So I know negative 1, 1. I know 0, 0, and I know 1, 1. Okay, so then I'll write my formula for my mapping. The x's are the inside of the cubed. Looks like it's just, so it says x minus 3, which means I'm adding 3 to the x's. And then I'll go with that, replace the y trick. So negative y plus 4. And then I'll just make my list of ordered pairs. All right, so starting with negative 1. Negative 1 plus 3 is 2. 0 plus 3 is 3. And 1 plus 3 is 4. And then negative y plus 4. So negative 1. Oh, you know what? I'm actually wrong. I'm sorry. I apologize for this. There's actually a negative on that one because the original parent graph has a sort of this shape to it. So it should have a negative y component. So I apologize if I set you astray. All right. So now that I did that, haven't made a numerical mistake yet. I just didn't write the negative. All right. So a negative y plus 4. So a negative 1 is 1 plus 4, so that's 5. 0 plus 4 is 4. And this one is 3. Okay, so then we're going to plot those. So 2, 5, 1, 2, 3, 4, 5 right there. 3, 4, so 1, 2, 3, 4. And 4, 3. 1, 2, 3, 4, 1, 2, 3. Okay. And then I have to remember that there's a curve to it. And so my graph should look something like that. One of our transformation questions is about non-traditional ones, so something that can't be described as a parent function and still understanding what it's asking us to do. So in this particular picture, the first thing I would do is I would make a list of the ordered pairs in the picture. So let's see, like this ordered pair looks like it's -4, -3. So -4, -3. Then that ordered pair looks like it's -2, 3. And then we have 0, 3 for that ordered pair. And then the last one would be 4, -3. Okay. And so what I'm going to do then is with these new mappings, I'm just going to apply that to these points. So f of x plus 2 plus 3 says take the original points and the x values. Okay, remember whatever we see is opposite of what we see. So it says plus 2, but I'm going to subtract 2. And the y values, again, I can come in here and write a y. It's just going to be y plus 3. So I can go into all 4 of my points and do that transformation. So if I take, what's -4 minus 2 is -6. -2 minus 2 is -4. 0 minus 2 is -2. And 4 minus 2 is 2. Okay, and then I'm going to go do the y's. So -3 plus 3 is 0. 3 plus 3 is 6. Another 6. And another 0. Okay, so then I'm just going to plot those points as best I can. So -6, 0, 1, 2, 3, 4, 5, 6 right there. -4, 6, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6 right up there. -2, 6 right there. And 2, 0, which is right there. And then I will connect those points. Okay, now you're probably thinking, hey man, that doesn't look like the same picture. It actually is. This graph, the original one that I got my points from, is a lot wider. So if the boxes shrink on you, then it might not look quite the same. All right, and then got to do the other transformation. Let's see if I get the ordered pairs. Okay. So here the mapping is x comma y 2, and it's inside. So if you remember, inside is opposite of what I see. So actually, even though it says times 2, my x coordinates are going to divide by 2. And then if I want to do the y thing, then it's going to be comma -y. All right, so all of my x's are half of them. So let's see, -4 over 2 is -2. That would be -1. That would be 0, and that would be 2. And then all my y values are opposite. So 3, -3, -3, and +3. All right, then I'll go plot my points. So -2, -3 right there. -1, -3. 1, 2, 3 right there. 0, -3. And 2, +3. 1, 2, 1, 2, 3. Okay. And again, it looks scrunched in because that's actually one of our transformations, is when the x values get shorter like that. Okay. All right, next up is to read some information off of a rational function graph. And all right, so domain. So looking at our pictures, let's see, looking at the x-axis, it looks like the only place we don't have an x value is this asymptote. So right there at negative, make sure I read that right. Looks like that's at -3, and that's at +3. So I want to kick out -3 and +3 from the domain. So -3 union, -3 to 3, union 3 out to infinity. Okay. As far as range goes, you can see that there's an asymptote that it's approaching at -2, and this curve actually doesn't go below -1. So my range is going to be anything from -infinity up till -2, and then since there's a missing section from -2 to -1, I'm not going to start my range back up again until -1 up to infinity. Intercepts. Okay, so we might have to do a little bit of estimation. I'll kind of take a little bit of leisure with my graph so I can see there's 3 places where it crosses. And I'm going to, I know I'm estimating, so again, it's going to be a lot clearer on the actual test, but I'm going to say that it crosses at -2, 0, at +2, 0, and on the y-axis it crosses at 0, -1. Horizontal asymptote, that's that flat horizontal line at -2, so that's the equation y equals -2. The VAs would be the -3 and the 3. Now those are actually equations, so those aren't numbers, those are lines, and so lines I actually do want to put x equals with both of them. And I don't have an example of an oblique in this picture, so that one would be none. All right, in number 10, one of the first things I want to do is I want to factor this. And the reason I want to factor it is the factored form actually lets me make some quick decisions about some of the characteristics of my graph. So looking at the denominator, that's about the only thing I can factor, so that would be x minus 2 and x plus 2. Okay. So as far as domain goes, what I'm going to kick out is anything that would make the fraction say 0. And so that's where the factored form is really nice, because I can quickly see that 2 and -2 are going to be excluded from the domain. So -infinity up, let me try that again. -infinity up till -2, and then -2 out to +2, and then +2 out to infinity. Vertical asymptotes, those would be the exact same numbers that I am kicking out of the domain. So x equals -2 and x equals +2. Horizontal asymptotes. Okay, so this thing is what we consider to be bottom heavy. So all bottom heavy rational functions have a HA, or horizontal asymptote, of y equals 0. X-intercept, I get that by looking at the numerator. So if I essentially set the numerator equal to 0 and solve, I get 0, yay. So it crosses the x-axis at 0, 0. And then normally, to find the y-intercept, we would plug in 0, evaluate it at 0. But it just so happens that when you take 0 and divide it by who cares, you get 0. So the y-intercept is 0, 0. Okay. Then we have this interesting question about, does it cross the HA? So I'm going to take the number I got for the HA, which was 0, and then I'm going to set my rational function equal to that and see if anything solves. So x squared minus 4. And one way to sort of think of this, I want to get rid of the fraction, so I'm going to multiply both sides by x squared minus 4, which will give me 0 equals x. So what that means is it does cross the HA at 0. And since we already know the ordered pair that that's associated with, that's 0, 0. Okay, so now I'm going to go in and sketch these things. And I might not have enough information for the picture, but we'll kind of cross that bridge when we get there. So in class, I said you want to start with any asymptotes and ordered pairs that you know of. So I know I got a vertical asymptote at -2. So I'm going to do these red lines with it, and another one at +2. And I know I've got an HA at 0. All right, and then ordered pair, so I know at 0, 0 there's an ordered pair. And that's pretty much the only thing I got. Okay, so what I don't know is I don't know around that ordered pair what's going on. So I have to test a bunch of places. So here, on the very far left, it could either be above or below. Same on the far right. I'm not sure. So what I'm going to do is I'm just going to pick a number that's clearly on that side. So say something like -5 and +5. And then I'm just going to evaluate it. This is where factored form is really nice. So x equals -5. I get -5 over -5 minus 2 and -5 plus 2. Okay, so let's just think out loud to ourselves about positives versus negatives. Up top, I have a negative number. In the denominator, I have a negative and a negative. So what happens when you multiply a bunch of negatives together? You get a negative. Okay, so going back to my picture then, that means I have to be below the x-axis. So my graph is going to hug below the asymptote. And let's do the same thing for 5. So if I evaluate it at 5, I get 5 over 5 minus 2 and 5 plus 2. And then we'll do the same sort of analysis. I have a positive number, positive, positive. So what does that mean? It means it's positive, and so it's got to be above the asymptote. Okay. What's going on in the middle? Does it come from the top or come from the bottom? Does it end at the top or end at the bottom? Right? So again, I'm not sure, but I can test some numbers. So I'm going to test -1 and 1, and just again get that quick sign as to whether or not it's above or below. So let me try -1 here. So -1 would be -1 minus 2 and -1 plus 2. All right, so again, quick little sign check. I get negative, negative, positive. Ooh, overall, what's that? That's a positive result. Okay, so that means I've got to be coming, so at -1, it's got to be above the asymptote. So we'll come in that way. It'll look like that. Now, I suspect, because there's a lot of symmetry here, that it's got to be below, but let's test it. So if I go x equals 1, I get 1 over 1 minus 2 and 1 plus 2. And again, we'll just put the signs in. That's positive, that's positive, negative, positive. So I have 2 positives and 1 negative, which gives me a negative. And that actually does exactly what we thought it would. So it's got this nice little, kind of looks like a cubic in the middle there. Okay, let's go down below. Look at the next one. Not a lot of factors. Actually, there's no factored form that I can fill in. Domain-wise, I do want to figure out where 2x minus 3 equals 0. And that's at x equals 3/2. So I don't want 3/2 in my domain. So -infinity up till 3/2, union 3/2 to infinity. So that's also my vertical asymptote, 3/2. HA, okay, this is what we consider to be a same case. So in the same case, I look at the highest exponents and I look at their leading coefficients. So in this case, it's y equals, up top I have a 1 over 2. So y equals 1/2. X-intercept, I look at the numerator. So x minus 5 equals 0, which is 5. So it crosses at 5, 0. Y-intercept, I want to evaluate at 0. So 0 minus 5 over 2 times 0 minus 3, which is -5 over negative, so positive 5/3. Okay, and does this cross the horizontal asymptote? So let's see, let's take our HA, so 1/2, and set it equal to our function. All right, let's see if we actually get a solution of some kind with this. So I think we'll just cross multiply. Let's do that. So 2x minus 3 equals 2 times x minus 5. So 2x minus 3 equals 2x minus 10. And I'm about to find an issue. When I put the x's together, the x's disappear, and I'm left with negative 3 equals negative 10. Well, that's false. So what does that mean? That means it does not cross the HA. That's actually very helpful. All right, so let's go plot some stuff, starting with any asymptotes. So VA at 3/2, so that's 1.5 right there. HA at 1/2, so again right in the middle there. Intercepts, let's see, 5, 0, so 1, 2, 3, 4, 5 right there, crosses. And at 0, 5/3, let's see, 5/3 is a little bit more than 1. It's 1 2/3. So that puts it right about there. And I know some things about my behavior. So I know it's got to hug the asymptotes, and I know it doesn't cross it. So it's got to go up. Now I'm thinking it could go up or could go down, but remember it doesn't cross the asymptote, so it's got to go up. It has to. Otherwise I would have found an ordered pair where it crosses. Now that way it's going to hug it, and then this way, same thing, could go up or down, but again, I know it doesn't cross it, so it's got to go down. So knowing that it goes down actually is very helpful as far as the graph is concerned.